Okay, looks like it's working now. So let's just solve another problem. Sharing my screen and choosing the right layout, and let's just go. Okay, setting the timer for 20 minutes. Signature. Nums is a list of integers, and then k is an integer. And we are returning a number, so we are returning an integer. Good subarrays of nums. A good array is an array where the number of different integers is in that array is exactly k. Okay. This is strange. The problem is a hard one, but to me it looks like a two-pointer problem. But let's maybe mention some challenges that arise, right? So we need to know the number of instances for each number in a subarray. And for the solution, I will also add an observation here. When growing or shrinking the array, it will change smoothly, like e.g. 1 unique, 2, 3, 2, etc. So we can just jump one step at a time. So that means that if we have k things, then we will need to just try to keep it at k and grow our array until it becomes impossible, and then shrink our array once it becomes impossible. So, okay. Maybe there are a few more issues that we need to cover, like off by 1 errors, how exactly to shrink, but that's fine. I think we can figure this out, yeah. Okay, so tests. Let's do 1, 2, 3, 2, 4, 1, and let's say k equals 2. Then let's just check all the possible subarrays that have exactly. Let's do 3 different numbers, right? Okay, so if we have 3, then we have this, and we have this. No, this doesn't work, that only has 2. But if we increase to this, it works. And then we cannot grow it even further, because then it will be again 4 numbers. So we have to do something like this. It's also 3 numbers. and then here is 3 unique numbers in the array. So overall, there will be 4 possible such subarrays. Another observation. So basically, it's the same observation about growing and shrinking, that can grow indefinite until there are more unique than needed, then can shrink until there are fewer unique than needed. So what I'm trying to say here, right? The challenge that we are observing is that we start by growing the array and we count the unique numbers in this array. We can do it in a dictionary, counter dictionary, and length of keys. Length of keys will be k. So we grow it until we get exactly to k, right? Then at this point, the problem becomes that we can start shrinking it too early. Let me show something like this. So 1, 2, 3, 3, 3, right? So how many, let's say we need to have 3 unique numbers. So how many such subarrays do we have? We have this is the first one while we start growing. Then this is the second one, or let me say we should continue growing this until while we can. So then we have grown, and let's say that we have 4 here in the end. Let's see. So we have grown it until we cannot grow it anymore, and then we start shrinking this array, and we shrink it to this, and that's fine. But what if we start growing it again here, right? Because what do? We need to kind of go back and shrink it back. That's the challenge of this problem, because we have another array of 3 numbers here, right? So all of those arrays are suitable, and we need to consider like both of these positions and both of these positions. And then how do we track something like this? And yeah, that's the biggest complexity, because it's not just 2 pointers. You cannot change the 2 pointers. You have to keep track of all these duplicates. But fortunately, this situation only arises when we have duplicates. Okay, but having said all that, let's just add this last array here, and the total number of the arrays with k unique numbers will be 5. Okay, how do we deal with those starting duplicates and ending duplicates? So the only situation that arises is that we need to keep track of duplicates, but we don't care how many, like, we can kind of merge this whole array in such a way that we combine all the duplicates, and instead we keep the value and its count. Then once we start iterating over the array, we will figure out that, okay, here we have one duplicate, here we have another duplicate. We just multiply the duplicate number on the left to the duplicate number on the right, and we get the total number of the arrays that we need to add. So reformat the array to value count of value in sequence. Okay, so then this algorithm that we are discussing, it will be a linear one. We are reformatting the array in of n time, and then two pointers will always also be iterating just like to one side. So this will be of n runtime and of n space. And let's start with the implementation. Current is equal nums. Can we just assume that we will never get an empty array? Let me just check. Yes, we can assume that. That's nice. So current num will be nums of should I create a separate subfunction? Yes, I think so. Def compact how to call it? It's like compress. Yes, compress self nums, and nums is a list of integers, and we will be returning a list of tuple of integers. So let's instead do it here, and let's call it compressed nums. So current nums, it will be nums 0. Current count will be equal to 1 for num in nums. If num equal to current num, current count plus or equal to 1. Else we do what? First of all, we do compress nums, append current num, current count, then current num equal num, current count equal current count equal 1, and then in the end we need to do it once more because we are not doing it for the last element, and we return compressed nums. Okay, so that's the first operation. Let's do compress nums, self compress nums, and now it's just a two-pointer problem. So and we don't even need to store it in a dict set, is just fine. So current nums will be a set, and for we will also know that the nearest no, it cannot be set, because even now we can have something like 1 1 1 1, let's say 1 2 2, then 1 2 2 again, and then 3, and then 3, and then 4, whatever, right? And let's say we need to say 3, so we will have to know that there are actually 2 2s here and then also 2 2s here, so that we process all that correctly. Once we start dropping 2s from the end, we need to know that it's just like one of the 2s that is dropping, or one of the ones. Just to be clear, by the way, how our compressed number will be looking. So there is just 1 1, then there are 2 2s, then there is 1 1, then again there are 2 2s, and then there are 2 3s, and then there is 1 4 1. So this will be the compressed array. Okay, so current nums will be dictionary. For right, we will have right and left pointers. So for right, and num count right, num right count right in compressed nums. So what do? We increase the count we are always adding our num right num. So current nums there, current nums get num there 0 plus 1, and then while length of current nums keys is bigger than k. So while it's bigger, we need to remove items one by one from the left. So left will be pointing to the beginning and at the start. So num L count, L will be compressed nums of L, and current nums, and we will definitely have this number there. So this will be minus or equal 1 if current nums of this equals 0. So we have removed all such elements. We delete this element in the array, and that's how we make the amount of keys smaller. So then, after we did all that, we now have our left and right numbers pointing to the leftmost and rightmost element that we need. And then for those duplicates, we just need to count the total number. Okay, 20 minutes have passed. We are on the right track so far, unless I'm missing something. So we also need to calculate total, that is 0. And here, if length of, if this is equal to k, because it can be smaller than k in the beginning when we are just increasing the size of our array, then we do total plus or equals count L times count R, return total. So this is the implementation. Let me also think about the corner keys. Let's say here, right, there will be just 1, and let's say something like this, 2, there will be 0. So let's first figure out whether we process those things correctly. So, okay. Actually, yeah, I don't think that we are processing correctly such things, right? Because then yeah, what if we have something like 1, 1, 2? So if the length is equal to 1, we just need to return. If k is equal to 1, we return length of nums. Because each of those will have, like, each of the unique numbers is a subarray with one unique number. Then if k is bigger than the length of subarray, we need to return 0, but I think we have 0 by default, and then we just never get to this. So we will be returning the correct thing for this edge case, and this edge case is basically the same as this one. Okay, so for edge cases we are fine. Let's now check some stupid simple stuff, like that. For example, we have added self where we needed to add self. Okay, we are returning things and correct things from the array. Okay, in our loops we are updating, we are adding this last element, and current count we are updating the num, updating the current count. We are appending to compressed nums. Okay, here it looks well. So here we do, here we are not updating things, right? Oh no, we are updating things. We are removing elements here. So we will not get into the never-ending loop, will we? Yes, because we can just continue removing. Oh no, we are not updating things correctly. Exactly, right? So the problem is that we are never updating L. So once we figured out what to do with this L, we do L plus equal to 1. So that was a bug. I don't need to find minimums from maximums. Okay, so I think this is fine. Let's now go over this example, and let's see what will be the result. So we are going here, we are going here, and we want to just compress the numbers, right? Oh yeah, another bug. We need to start at 1 here. Thing I have forgotten to do, but wanted to do. So compressed nums. Here we will start with empty list, and then current num will be 1, and current count will be also 1. Then starting at this element, we will be adding, okay, current count 8 is equal to equal num, so we do 2. We move here. It is not equal, So we update compressed nums with current num and then current count. Okay. Then we update current num to 2 and current count to 1, which is good. Then we continue here and the next one is 3. So we again update this with number 2, count of 1, and current number becomes 3 and count becomes 1. And then we move here, we update this count, it becomes 2, and then we move here, it becomes 3, 4, 2, and then finally we are out of this loop, but we need to add the final last update. We have updated also this, and now we are updating for 1. Okay, so these are our compressed numbers. This is fine. Exactly what we were expecting. Now we need to continue here and figure out what's going on down the line. Okay, so let's also create the right and left pointers here. So right pointer and then left pointer. So right pointer is moving first, that's why it's at the top. So our number count compressed. Current nums get. Okay, so first of all we do current nums, and current nums for value 1. Oh, we actually don't ever need our R, right? Yeah, let's just remove it then. So for because here we don't need to control for L is smaller than R. It will always be smaller than R. Okay, so here we are storing first 1, and we are storing that the count is 1. Then we are continuing. We try to length of current key is bigger than k, but currently we have just 1 key and the key is 3, so we are not doing anything. So R moves here, and then we count that 2 is also 1, and number of keys is still not big enough. Then finally we move here, and 3 also points to 1. And here we already are at the point where we need to multiply the numbers. So it's not bigger than k, it's equal to k. So it's exactly equal to k. We do total plus or equal count L times count R. So finally we are updating this to 4. And then finally we are moving to 4, and there is just 1 4. And here we will be checking that finally we are getting in this loop, and we have 4 keys, which is bigger than k. So we are finally pointing to this, and we start decreasing current nums of num L. Num L is 1, so it's -1, so this becomes 0. And if it becomes 0, it gets deleted. And if it gets deleted, then we get again just the length of 3 there. So then this is deleted, we do L plus 1, and here we increase by our, it's exactly equal to k again. So we multiply, we multiply count L by count R, and count L will be 1. Oh, sorry, we moved here already. And count oh, that's another issue, right? Almost correct, almost, but we need to update our value num and count L. Yeah, otherwise it was the previous one. So number file and counter file is compressed nums, and total will be this. So we multiply 1 by 1 and edit, and this will be 5, and this is finally correct as long as I'm concerned. But yeah, a lot of tricky things. Made a lot of mistakes. Expected. Yeah, that's cannot unpack non-iterable object. Oh, I wanted to enumerate those, but I don't need R, so I'm not enumerating those. Oh damn. So we are always underestimating the number of one, two, one, two, one, two, one. Yeah, looks like there is another edge case, right? Oof. Okay, I see why this is a tough problem. So 1 to 1, and we want 2. So what will it be for us, right? Yeah, here the problem is that we will be storing our numbers as 1, 1, and then 2, 1, and then 1, 1 again. And we will figure out that here we have one number, and here we have one combination of numbers. But yeah, I think actually I know how to change that. The problem here is that we are stopping at each R. We don't need to stop for each R. We need to increase the R as far as we can. Otherwise, we won't be counting some of the issues, which is not a big change. We just need to do this. R equals to 0 and L equals to 0. And while length of current nums keys is smaller, okay, so we basically need to stop in our R exactly in the moment yeah, so how do we stop there? If we want to stop this last element, this last 3, right? So already here we will have different elements, and we need to check So the challenge that I see now, right? We can easily check whether the next element exists. In the bounds. So we can check that while the element is already in our dict here in current nums. So the thing is that moving R can only increase our dict. And if we know that the next number won't increase it, then we need to increase it. So how do we check that next number won't increase it? So let's say R starts at -1, while compressed nums R +1 while this is smaller than k. Or we will continue increasing this until unless it's the last number. So here we need to do r plus 1 smaller than length of compressed nums and compressed nums in current nums. Okay, so this is ugly, but it should be a workable solution. So what I'm trying to say here, right? If the length of current keys is smaller than k, then we can definitely add whatever is the number. We need to first, okay, we also need to first move the number. So we do that, we do r plus or equals 1, so that we start adding at the 0th element, and then num r count r will be equal to compressed nums r, and we are updating everything without any changes. So if it's smaller than k, then we definitely need to add whatever the number is there, the next one. If it's not smaller, if it's equal, if we already are, for example, at this 3, right? Sorry. Let's focus on this, right? So if we add it here, yeah, we are not. But damn, yeah, it still doesn't solve our problem, right? What else can we do? We can calculate it here. And then we can also continue iterating our R. And we should calculate it there. Yeah, how about calculating everything to the left of it? So here we need to return 3, because it's 1, 2, 3. So for this, for example, we can just count 1, and then we can move here, calculate 1 again, and then start moving the left and calculate 1 again. Yeah, I think this should be the process, but I don't have time to implement this anymore. So first of all, yeah, I probably shouldn't have started changing this code. Okay, let me introduce this code. And then let me remove that. Paste it as a separate thing. Okay, so let's do it like this, and then copy from here and do it like this. Should have started with that, but now, okay, this is 40 minutes. And now, I will probably pause because I have just 5 minutes. But I think this is the idea, right? That we try to calculate whatever happens to the left of every number, and then we to the left of any right pointer, and we try to change the left pointer all the time, because sometimes, yeah, that's basically another issue, right? What if we are pointing like on the left and on the right, we have the same number, but then there are numbers in between that make it overall a valid number of k. Okay, I digress. Looked like an easier problem than it turned out to be, a true difficult one with many corner cases and ideas, and I have also approached incorrectly this correction in the end. I should have thought it through better, should have figured out an algorithm. But I think it's also like just another option here is that we can either drop things on the left and still be fine, or drop things on the right and still be fine. That is, if we don't have even more of those ones inside. Oh, this is ugly. What if you have something like 1 1 2 2 1 1? Okay, I do need to drop. It was an interesting problem. Thanks everyone for staying here, whoever you are.